In this video, I'm going to talk about the rate law. Now, sometimes it's called the differential rate law, and that may make more sense later on when we talk about the integrated rate law, but for now, I'm just going to call this the rate law, and it's an equation that we can use to find the relationship between the concentration of reactants and the rate of the reaction. So we're going to need those two pieces of information, the rate of the reaction and how it relates to the concentration of the reactants. So the relationship, this is a formal definition, the relationship between the rate of reaction and concentration can be expressed in the following equation known as the rate law. Now, in this equation, A is going to be the concentration of the reactant, and the units for that will be moles per liter. We're going to use normal concentration units when we do anything related to concentration. K is going to be something called a rate constant. It's just something that is unique to each individual reaction, and it's just a number that allows this equation to work. N will be the reaction order. And we'll get to more about that reaction order. It's kind of the most important part here. The reaction order, we'll get to more of it later on. And then rate, of course. We're going to be using the units of molarity per seconds as our units for rate. Now, if we have a very slow reaction, then our rate units will be maybe molarity per hour or molarity per week. But for now, all the reactions we are concerned with are going to be in molarity per second. So we have rate equals this K times the concentration to the power of N. Now let's look at the reaction order. The reaction order, that's the N value. It determines how the rate depends on the concentration of the reactant. So if N equals 0, and by the way, these are all going to be integers for the purposes of this course. If N equals 0, then the rate doesn't matter, doesn't depend on the concentration. If N equals 1, then it's a direct correlation. The rate is directly dependent on the concentration of the reactants. And if N equals 2, then the rate is proportional to the square of the concentration. And I'll get to some examples of this on the next slide if you're wondering, what this all means. These are just definitions. Let's get to a graphical way of looking at this. So in a zero order reaction, the rate is equal to K times the concentration to the power of 0. And if we look at the y-axis here, this is the rate in molarity per second, and the x-axis has molarity as the concentration. So in a zero-order reaction, the rate, it doesn't matter. It's not changing depending on different concentrations. So it's completely independent of what that x value or that concentration value is. If the concentration increases, the rate stays the same. If the concentration decreases, the rate stays the same. So in a zero-order reaction, nothing happens to the rate as it corresponds to the concentration. Now in a first-order reaction, the concentration will increase, or as the concentration increases, the rate will increase, and it will be a direct proportion. So that means it'll increase by the same amount for every amount that the concentration increases. It's going to be there'll be a direct relationship. You'll get a straight line with a definite slope. Now in a second order reaction, you'll see it's kind of more of a quadratic or a curved slope. That means that when the concentration increases, the rate is going to increase by a square of that. Now let's take a look at how this relates to some experimental data. And one thing I'm probably going to say several times is that the reaction order can only be determined by experiment. So this is called actually the method of initial rates. And let's take a look at the first set of examples. If we take a look at the concentration, so we are doubling the concentration. We have lots of different concentrations. What happens there is that the initial rate in molarity per second doesn't change. So we've doubled the we've increased the concentration, and nothing's happened to the rate. This shows us that the reaction order is 0 and that the rate law for this reaction is K times the concentration to the power of 0. So this is a zero-order reaction. Let's look at this second example. If we increase the concentration by 2 times, the initial rate increases by 2 times. And if we increase the initial concentration by 3 times, then the reaction rate increases by 3 times. So we go from 0.15 to 0.45. This is a direct relationship. So this is a first order reaction, and the rate law would be written as rate equals K, or that constant, times the concentration to the power of 1. So that's how we would write that rate law. Now let's take a look at the last example. If we increase the initial concentration by 2, then what happens is the initial rate increases by a factor of 4. And if we increase the initial concentration by 3, the initial rate increases by a factor of 9, or the square of what we did to that concentration. This would indicate we have a second order reaction, and all you guys need to be concerned with are 0, first, and second order reactions. So the rate law would be written as rate equals K times the concentration to the second power, or squared. Now, real data is not always as clean and perfect as this, and if you're having trouble eyeballing this information, this data, and that's kind of what I did here, is I sort of just eyeballed it. This goes up by a factor of 2, this goes up by a factor of 2. If you're unable to do that, there is an equation that you can use, and that is if you compare the rate of one whole entire line of data and the rate of the second whole entire line of data, and you compare the rates with the values that come after that equal sign. So here I'm just going to set this up for you. So I'm going to use experimental data from the second order reaction. And by the way, those K's, you notice they cancel out. I'm going to use 0.30 as my concentration, and that means that 0.135 is my rate. So I'm going to put this into those proportions. It's really just finding proportions. And then I'm going to use 0.1, and you can use any line of data that you want. I'm going to use 0.1 as the concentration and 0.015 as the rate. So I'm plugging this in. And by the way, if we multiply both of those, or if we take those both to the x power, then what we can do is we can just put those in parentheses to the x power. And if I divide this out, what I get is 9 equals 3 to the x power. Well, the x, if I solve for the x is equal to 2. So 3 squared is equal to 9. So not only can the reaction order be determined only by experiment, but the rate constant can only be determined experimentally. So I'm going to use information from our previous example here. I'm going to look at this first order reaction and the first line of the first order reaction. Basically, all you need to do here is substitute in your values for the concentration and the rate, and then just solve for K. So I'm going to use the rate law here and just solve for K. So the rate is equal to 0.015 molar per second, and that's equal to the K, which is my unknown in this situation. And the concentration that coincides with is 0.1 moles per liter, or 0.1 molarity. And that's raised to the power of 1. So I'm just going to really leave that off. Now what I'm going to do is take both sides and divide both sides by 0.1 molarity, or multiply by 1 over 0.1 m. And that allows me to cancel out both of the 0.1s on the right hand side, and I get K all by itself essentially. One thing I'm going to do here is I'm going to cancel out the m's, and you'll see that the s doesn't go anywhere. That's going to be important. Just a second here. So 0.015 divided by 0.1 is equal to 0.15, and that's my K value. Now the units for that are what remained, seconds to the negative 1. So K equals 0.015 seconds to the negative 1, and that is my rate constant for this reaction at this specific temperature. And by the way, back to the units on this, s to the negative 1, those are the units you get for your rate constant when you have a first order reaction. If you have a 0th order reaction or a second order reaction, you're going to get different units on your rate constant, because different units have to be involved in canceling out. So your rate and your concentration have the appropriate units. So for a 0 order reaction, the units are going to be molarity per second. For a first order reaction, the units are seconds to the negative 1, or per second. And for a second order reaction, you're going to have molarity to the negative 1 times seconds to the negative 1, or per 1 over molarity times seconds. So you can write it either way. Let's take a look at reaction orders when we have more than one reactant. And you'll notice in this generic equation, I don't care what the products are. All I care about are the reactants, what I'm starting with. So if we have a rate or an equation that has A and B, and by the way, the coefficients would be lowercase a and lowercase b, the rate law is written as rate equals K times the concentration of A to the m power, whatever that reaction order is, times the concentration of B to the n power. And m and n can only be determined by experiment. Notice how the lowercase a and b, the coefficients, have no place in this rate law. There's no way you can look at a chemical equation and know what its rate law is. You can only determine that using an experiment. So let's take a look at some actual experimental values with reactions that have more than one reactant. So A and B here. What we need to do is we need to find a situation where if we're solving for A, then all the B's need to stay the same. And if we're solving for B, then all the A's need to stay the same. Just because we can't change more than one variable and really know how it affects the reaction rate, and you'll see what I mean by that when I actually start solving this problem. So we have A and B, and they're creating products. Now my generic rate law, I'm going to write it out. Rate is equal to K times the concentration of substance A, and that's going to be to the power of m, we don't know that information, times the concentration of substance B to the power of n. Now the first thing I'm going to do is I'm going to figure out what m is equal to. So what is my reaction order for A, for substance A? And when I do that, I need to find situations, or if I need to find data where B remains the same. So all I'm doing is just looking at my A information. So if I look at trials 2 and 3, the B's stay the same. The concentrations of B are both 0.5. So I'm going to use trials 2 and 3 to figure out my information for A. So my information for A is 0.30 and 0.60. Now if I go from 0.30 to 0.60, that increases by a factor of 2. So that doubles, I'm doubling the concentration. Notice how B is staying the same. And what happens to my rate when I double the concentration? Well, I go from 4.8 times 10 to the negative 2 to 9.6 times 10 to the negative 2. Well, from 4.8 to 9.6, that's double. So if my concentration doubles and my reaction rate doubles, that shows me that this is a first order reaction because the concentration and the rate are directly related to each other and it's linear. So M is going to equal 1 for this reaction. Now I'm going to take a look at B and I'm going to try to solve for N and figure out what the reaction order for B is. So I'm going to do this one in red. And now I need to find two scenarios where A stays the same. So trial 1 and trial 2, A is staying the same. A is 0.30 molarity there, and B is what's changing. So I have trial 1 and trial 2 are what I'm going to be comparing. Now B, if I increase B from 0.25 to 0.5, what does that do to my rate? Well, first of all, increasing from 0.25 to 0.5, that's doubling my B. What does that do to the rate? That increases it from 1.2 to 4.8. That increases it by a factor of 4. That means that this is a second order reaction. So N is going to equal 2. So that superscript there, or to the power, that power is going to be 2. Now I'm going to rewrite this rate law with the correct reaction orders in it. So rate equals K times A to the power of 1, the concentration of A to the power of 1, times the concentration of B to the power of 2. Now what I'm going to do is I'm going to solve for K. And when I do this, I can literally pick any one of my trials. I'm just going to do it with the first trial, but you can pick any one of your trials and substitute in the information and solve for K. So using trial 1, the rate is equal to 1.2 times 10 to the negative 2. And that is M per S, so molarity per second. The K is what I'm trying to find. And then I'm going to substitute in my concentration for A, which is 0.30 molarity. And that's raised to the power of 1 because this is A reacts in a first order way. So independent of B, A is going to be first order. And then I put in my B, which is 0.25 molarity, and that is going to be second order. So B reacts in a second order way. By the way, the overall reaction order here is 3, in case you're wondering. It's the sum of the exponents. So what I need to do here is I need to solve for K. I have all of my numbers in there, and it's just kind of like a plug and chug at this point. So the tricky part is really getting your units kind of down. That's where knowing the overall reaction order helps. So we have 1.2 times 10 to the negative second m per s equals K, and I'm just going to kind of put all of this together here. We have 0.30 molarity times 0.25 times 0.25, or to the second power is 0.0625 m squared. And the next thing I'm going to want to do is I'm going to multiply the 0.3 m times the 0.0625 m squared, 0.01875 m cubed. All right, so now what I'm going to do is I'm going to divide each side by 0.01875 m cubed. So divide both sides here by the same number so I can get K all by itself, essentially. Or I can multiply it by 1 over 0.01875 m cubed. And you'll see here that that m on top there cancels out, and then what we have left over is m squared is going to remain. So if I take 1.2 times 10 to the negative 2 divided by 0.01875, I get 0.64 m to the negative 2 because it's on the denominator, s to the negative 1 because that's also a denominator. So if they're denominators, you can put them all in line as long as they have the negative power. So K is equal to 0.64 m to the negative 2, s to the negative 1, because the overall reaction order here is a third order reaction, so the units are going to be a little different for that K. Now what I'm going to do is I'm going to rewrite the entire rate law, including that K value. So the rate is equal to 0.64 m to the negative 2, s to the negative 1, and that's my K, times the concentration of A to the first power times the concentration of B to the second power. And I can use this to figure out the rate of my reaction with any amount or any concentration of A and B. So let's try another example here. Determine the rate law for the following reaction using this experimental data. We have nitrogen dioxide reacting with carbon monoxide to create some products. We don't really care about the products. We just care about the initial concentrations for each of these ingredients, for just the reactants. So we have NO2 and CO are our ingredients. So I'm going to write out the generic rate law here. Rate is going to be equal to K times the concentration of NO2 to some power, we'll figure out what the reaction order pertaining to NO2 is, times CO to some power N. We don't know what the N is. We don't know what the reaction order as it pertains to carbon monoxide is, but we will figure that out. And now if I want to figure out the M first, we'll figure out what the reaction order pertaining to NO2 is first. And we need to find two sets of data where carbon monoxide stays the same. So it looks like trial 1 and trial 2 are good for that. So I'm going to use trial 1 and trial 2 to compare my NO2 values because my CO values remain the same. So I'm just going to highlight here the rates and the concentrations that I'm interested in. Now if I double my concentration, what happens to my rate? It goes up from 21 to 82, or 0.0021 to 0.0082. That increases this by nearly a factor of 4. So what that tells me is that M is equal to 2. This is a second order reaction as it pertains to NO2. By the course of just the NO2, if you individually look at the NO2. Now let's look at the carbon monoxide. So I need to find two trials where the NO2 stays the same, and it looks like trials 2 and 3, the initial concentrations of NO2 remain the same. So I'll highlight the data that I'm going to use here, and it looks like my carbon monoxide concentration doubles from 0.1 molar to 0.2 molar. So if I double my initial concentration of carbon monoxide, what happens to my rate? Well, nothing. Nothing happens to my rate. It increases by nothing. There's no factor that it increases. It doesn't double or triple or quadruple or anything. So that tells me that the carbon monoxide concentration has no effect on the overall rate of reaction. I could have any amount of carbon monoxide and it would not affect the amount of the rate of the reaction. So the reaction order there is 0. I'm going to rewrite this whole rate law here. So I have rate equals K times NO2, the concentration of NO2 squared, times the concentration of CO to the 0th power. And actually, anything to the 0th power is equal to 1. So I basically can leave that out of my calculation for my rate law if I wanted to, because it doesn't impact the overall course of the reaction. It doesn't impact the rate of the reaction. So I'm going to use trial 1 to solve for K. So I'm plugging everything in here. I have 0.0021 molarity per second equals K times 0.10 m squared. I'm going to leave out the CO stuff. I don't need that. So 0.10 squared is 0.01, and m to the second power is m squared. So I'm going to take both sides and multiply by 1 over 0.01 m squared. And I'm just rewriting this to show that information. And that is going to equal K times 0.01 m squared times 1 over 0.01 m squared. So I'm really just showing you how I'm canceling out that 0.01 m squared stuff. So that cancels out, and then my m's are gonna some of the m's are gonna cancel out on the left hand side. 1 m and then one of the m's in my from that I moved over to the other side. So what I end up with is K is equal to 0.0021 divided by 0.01 equals 0.21 m to the negative 1 s to the negative 1. That is the unit that represents a second order reaction. So everything's kind of making sense here. Everything checks out. We're good so far. Our units are good and our reaction orders are also good. So let's rewrite this including all of the information so we can apply it. We could apply this information to any amount of initial concentrations and be able to figure out that initial rate of reaction. So rate equals 0.21 m to the negative 1 s to the negative 1 times n, the concentration, the initial concentration of NO2 squared, and then I'm just going to put in the CO just to show that it is a zero order reaction as it pertains to the carbon monoxide, but overall a second order reaction.